On page 21, we're going to kind of extend what we learned in page 20. Whenever we do a optimization problem in math studies, you basically have like an independent variable and a dependent variable, kind of like you do in science. And you have control over the independent variable. You can change that independent variable to be whatever value you want to. The thing is, you want to make it the exact right amount so that the dependent variable is the highest or the lowest that it can possibly be. Okay? So the value that you're trying to optimize is the dependent variable, right? Now the problem with most math studies problems is at the beginning you don't just have one independent variable, you have a couple independent variables. And if you have more than one independent variable, how the heck do you graph it? Because the way we solve these problems is by graphing. We can only graph two variables at a time, right? So what happens is the two independent variables are kind of related to each other, and you're going to get rid of one just like we did on page 20, and then you're going to only have two variables left. Okay? So we're going to do that on three problems here. And just to remember what some of these equations are called, we have the main equation and we have the constraint equation. And the difference between the main equation and the constraint equation is the main equation has three variables total. One of the variables is the amount that you want to optimize or make the highest or lowest possible. And we have the constraint equation, which relates the other two variables that aren't the optimization variable. Okay? All right, so let's take the first problem, and it gives us two equations. It doesn't tell us what's what, of course, but just by the fact that the left one has three variables, a, l, and b, and the right one has two variables, l and b, we know that this one is the main equation, and the other one is the constraint equation. Okay, and remember the main equation is the one that you're going to put in the calculator once you reduce the number of variables from 3 to 2. Okay. So when we do that, we're going to do a little bit of painful algebra here. And the first thing we're going to do is, okay, it even tells us what it wants. It wants A in terms of L, which means on the left, we're going to have A equals something, and in the middle, we're going to have L somewhere. Okay, but do you notice there's no B's? They don't want B's. Okay, if you look at our main equation, we can see that we have A on the left side like we want, but L and B on the right side, we have both L and B. So we want to get rid of B, right? So how do we get rid of B? Now we're going to use the constraint equation, okay? The constraint equation has 3L minus 5B equals 18. We want to have an expression that gets rid of B, so we want to solve for B. So B equals blah, 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 L. Then we can put B in for this B, and then we'll get rid of the B's, okay? So let's figure out what this equation, the constraint equation, is in terms of B. So to do that, we're just going to rewrite it first. So we're going to have 3L minus 5B equals 18. Then we want to isolate the B. So first thing we're going to do is we're going to subtract 3L from both sides. And then we're going to get negative 5B equals 18 minus 3L. And then we're going to divide both sides by negative 5. And then we'll get B equals 18 divided by negative 5 minus 3L divided by negative 5. Okay? So we can use this equation, or this new equation, to substitute in to our main equation. And the main equation is 1/2 LB, but we don't want the B in there. We only want L's. So what we're going to do is we're going to take this relationship here, and we're going to put it into for B here, and then we're going to only have A equals something something B. So we'll have A equals 1/2 L times, and this expression for B, which is 18 minus 5, or 18 divided by 5, and let's make these into decimals. So if 18 divided by 5, which is 3.6, negative 3.6, right, because 18 divided by negative 5, negative 3 divided by negative 5, which is 0.6, plus 0.6 L. Okay, so now we're going to distribute the 1/2 L to both terms, and we'll have 1/2 L times negative 3.6. If you put 3.6 divided by 2 in the calculator, you would get negative 1.8. And if you would put 1/2 times 0.6 in the calculator, you get 0.3, so plus 0.3 L. And this would be L squared because I got L here and I have L here. Okay, so now we have an expression with A in it and L in it, which is exactly what they wanted. Now what we're going to do is we're going to put this in the calculator, and when we put it in the calculator, we want to put A as Y, and we're going to put L as X, okay? So let's do that. We'll go to Y equals. We're going to put in this expression, Y1 equals negative 1.8 X plus 0.3 L squared, so X squared, and then we're going to graph it. Okay, I actually had, not the zoom standard here, so let's see what it looks like with zoom standard, so I can show you if you need to do any adjustment of the window at all. Okay, in this particular case, it looks perfectly well behaved here. So it says to find the minimum value of A, and remember A here is Y, okay, and the value of B that corresponds to that minimum value. The value of B that corresponds to that minimum value, well, we don't even have B here. They told us to put A in terms of L, which we did, but then now we're going to end up figuring out the value of L that corresponds to the minimum value of A, not the value of B. But I'm going to show you how to figure that out easily, okay? So the way we have this set up, we can easily find out the value of L that corresponds to the minimum value of Y. Okay, we can do that by doing second calc min and finding this point, which will give us the L value and the A value at this point. Okay, so we'll do second calc maximum, which is number 4, and left bound we can do it just here, and then we'll move the cursor over to the right, and we'll hit enter again, and our maximum value is 4.696, which is the same thing as 4.70. So 4.70, which is the value for L. The X value is L, right? And the Y value is A. The Y value of A that corresponds to the maximum is negative 1.84. Negative 1.84. Okay? And now what we do is, okay, we want to know actually what the B value is that corresponds to this point. So to do that, we can use this equation here, because remember, if we put the L value on the right side, we can figure out what B is. So now we're going to do that. So we're going to take 4.70 and we're going to put it in for L here. And when we do that, we're going to get, let's see, remember that negative, or 18/5, we can write that as a decimal, which is 3.6, okay? So we'll have negative 3.6 minus, or plus 0.6, and our L value is 4.70, right? So now what we can do is we can figure out the B value that corresponds to the L value of 4.7. So we're going to have 0.6 times 4.7 minus 3.6. It's negative 0.78. Okay, that is the first problem. And now let's move on to number 13. So given 3y plus x equals 30, find the maximum minimum value of 2xy and determine its nature. Okay, when they say determine its nature, they want to know if it is a maximum or a minimum. Okay, so which one is the the constraint equation, which one's the main equation. If you look at these, they both have two variables, but this one does not have an equal sign. So actually, the maximum value, minimum value of this expression here, you actually need to assign another variable to it, like let's say area or something like that. A equals 2xy. So you can see that actually the second equation is the main equation because it's got three variables. Okay, once we make it into an equation, it becomes three variables, right? And this would be the constraint equation. Okay, so let's figure out the main equation with just two variables in it. The way we do that is we use the constraint equation to eliminate one of the variables. They didn't tell us which variable to eliminate, so why don't we just eliminate the easiest one? So what we're going to do is, if we have 3y plus x equals 30, isn't it easier to do x equals blah, blah, blah instead of y equals blah, blah, blah? And I'll show you why. If I subtract 3y from both sides, that's going to give me x equals 30 minus 3y, right? So that's already the constraint equation. And if I put this constraint equation into the main equation, I can get rid of the x value, the x variable, and I just end up with y. So I have 2x, or 2 times 30 minus 3y, and then I have that multiplied times y. And so if I could simplify it, or I could just leave it like this. Why don't I just leave it like this? One of the confusing things about this, and I'm glad this happened, is that I already have a y in this equation. And in the calculator, when I put this equation, now that I have the main equation with two variables, I want to put it into y1, right? When I put it into y1, the left side is y and the right side has x's in it. But if you look at my main equation here, the left side is a and the right side has y's in it. Now remember, this little y here is not the same as the big Y in the calculator. The big Y in the calculator is going to be the a, and the small y on the right side are going to be x's, okay? Because on the calculator, the independent variable is always x, and the dependent variable is always y. So we're going to rewrite a equals 2 times 30 minus 3y times y as in x's. So it's going to be 2. It's going to be 2 times 30 minus 3y, and instead of 3y, I'm going to put 3x, right? And then I'm going to put times x. And then I'm going to graph that. And then I'm going to see, okay, is this going to be, oh my gosh, it's so skinny or something. Oh no, it's just very tall. So let's do zoom fit. Do zoom fit and see if we can see it. Okay. See if this is better. A little bit better. Okay, so that looks like it's going to be a maximum point. So we know that it's going to be a maximum point, and we would like to find the value. So let's find the value. Of course, we're going to use second calc maximum because it is a maximum point. Oops, and the left will be on the left. The right needs to be on the right side. Moving over to the right side of the maximum, hit enter again. Doesn't matter what my guess is, and the maximum is 5, 150. So it's going to be 5, 150. The 5 corresponds to the small y, and the 150 corresponds to a. Okay? And it asks for the maximum value of 2xy. That's equal to a. So our answer is 150, and 150 is a maximum, right? Okay, let's move on to the last one. Now we have this equation here, and we have this equation here. Given that r plus h equals x, express r squared h in terms of r only, okay? Hence, find the maximum value of r squared h subject to the constraint r plus h equals 6. So, they're telling us that this is the constraint equation. That means this, big A equals r squared h, is the main equation. Okay? So, they're also telling us that they want the main equation with only r's in it. So the constraint equation, what we need to do is reduce it to this form. H equals something something with R in it. Okay, then we can put that in to here, and that would get rid of all the H's, and that's what we want. Just put it in terms of R. Okay, so let's take R plus H equals 6 and change it into H equals something something. First thing we're going to do is we're going to subtract R from both sides, and that gives us H equals 6 minus R. Once we get H equals 6 minus R, then we're going to put it into our main equation. And our main equation originally is A equals R squared H, but we want to make it so that there's only R's in it. When we do that, we're just going to use this equation, and we're going to put it in for H. So we're going to A equals R squared times 6 minus R. And so we can put that expression into the calculator as the main equation. And let's see, A equals R squared. So instead of A and R, what we're going to use is Y, X, and X. So we're going to have Y1 equals X squared times 6 minus X. And then we're going to graph it. We might need to redo the, okay. Let's go to Zoom Standard first. That should always be our first step. Some of these problems with optimization have like really weird scales. Where is it? Oh, it's 6. Let's see if this one works with kind of the standard scale. Kind of. The only problem is I don't see the top of this, okay? So if I want to see the top of this, then I could do a zoom fit. It's a 0, option 0. Okay. Okay. Maybe this is a little bit too high, so I'm going to change the window because like I can barely see my maximum here. I want a maximum value, so it would be around here. I can't really see it. So what if I make the maximum Y value like 50 or something? So let's do window and look at the maximum Y value. It's 1600, my gosh. I think that's a little excessive. What if I make it like 100? Okay, now we're going to find this maximum point. Of course, we're going to use second calc maximum, which is number 4. And then we're going to set the left bound on the left side of the maximum, and then we're going to go slightly to the right side of the maximum and set the right boundary. And our answer is 4, 32. So basically, 4, 32 means that the left number is X, or I'm sorry, the left number is R, and the right number is big A. So what are they asking us for? The maximum value of R squared H. The maximum value of R squared H is 8. So they wanted this number. And that's the answer, 32.